Welcome to the deep dive. So what we do here is basically take a stack of sources, dive deep, and pull out the key insights to get you up to speed fast, make you the most informed person in the room. And today we're tackling, well, the history of maths, specifically drawing a lot from Ian Stewart's brilliant book, Taming the Infinite.
Yeah, and our mission, if you like, is to look at those foundational bits, numbers, symbols, rules that seem totally baffling, maybe even dangerous back in the day. You know, the ideas people just couldn't accept, but which somehow now form the bedrock of, well, everything.
Right, because it's really not this smooth, linear story, is it? It's full of these intellectual battles, resistance to new ideas. It's a human story, really.
Yeah.
We're basically going from, people arguing about how to even write down the number 10, all the way to things like chaos theory, complex analysis, stuff we now use for, I don't know, quantum physics or even fine-tuning a pacemaker. It's quite the journey.
Okay, let's unpack that, starting right at the beginning. Notation, it just feels so natural now, our 0 to 9. But you're saying it's, what, relatively new? Shockingly new in the grand scheme of things, really. Our Hindu-Arabic system, the one we all use with the 9 digits plus 0, it only really became common maybe 1,500 years ago, give or take. And decimals, the little dot that lets us be so precise, that's 450 years old, barely yesterday, historically speaking.
Wow, okay. So what were people doing before that? How did, say, the Egyptians handle big numbers? Must have been messy.
It was. Well, messy is one word. Additive is the technical term. They had unique symbols for 1, 10, 100, 1,000, and so on. To write a number like, let's say, 5,724, you literally had to draw the 1,000 symbol 5 times, the 100 symbol 7 times, the 10 symbol twice, and the 1 symbol 4 times.
So just symbols repeated over and over.
Exactly. Up to 9 times for each power of 10. It worked, sure, but imagine carving that into stone. Tedious doesn't even begin to cover it.
Okay, so tedious. What about other cultures? The Babylonians, weren't they more advanced?
They were, in a way, much more abstract. They only used 2 basic wedge shapes in their cuneiform script. A thin vertical one for 1 and a thicker sort of sideways one for 10. But the clever part was their place value system, based on 60, not 10.
B60, like our minutes and seconds.
Exactly the same origin. But here's the tricky bit. The same symbol could mean 1, or it could mean 60, or it could mean 3,600, that's 60 times 60. It all depended on its position.
Right, like how 1 in 100 means 100, not just 1. But without a 0, how did you know if a symbol meant, say, 60? Or just 1, or if 3L601 was different from 61. That sounds ambiguous.
Hugely ambiguous. And that's the crux of it. That ambiguity points directly to this massive philosophical hurdle they faced. The idea of nothing as a number. If numbers count things, how can you have a number for no things? It seems contradictory, doesn't it?
Yeah, I can see that being a mental block.
For centuries it was. Civilizations sort of danced around it. The Babylonians sometimes left a gap, but it wasn't consistent. It really took the mathematicians in India, much later, to formally treat 0 not just as a placeholder, but as a number in its own right, a quantifiable concept.
And that clarity paved the way for, well, everything else in arithmetic.
Pretty much. It unlocked so much potential, but, solving one problem often creates another. As soon as 0 was kind of accepted, people bumped into negative numbers.
Right. Less than nothing. How did that go down?
Well, the initial push came from a very practical place. Money. Debt, specifically. Hindu mathematicians started using negatives to represent what you owed. The logic was, being in debt is definitely worse than having absolutely nothing, so it must be less than 0.
It makes sense from a bookkeeping perspective. But philosophically, still tricky.
Oh, absolutely. Massive resistance. You even had brilliant mathematicians like Bhaskara who'd use negative numbers in his calculations. He'd get an answer, maybe a pair like 50 and minus 5. But then he'd explicitly say you should ignore the negative one. Why? Because, and this is basically a quote, people will not accept them.
Wow. So the math worked, but the concept itself felt wrong, intuitively.
Exactly. It felt unreal. It took a long, long time for negative numbers to be fully embraced as just another part of the number line.
Okay, so we've battled 0, we've wrestled with negatives.
Yeah.
What was the next big impossible idea that really shook things up?
Now we head to ancient Greece, the Pythagoreans, and the shock of the irrational numbers.
Right, Pythagoras and his followers, they had this whole philosophy, almost a religion, built on numbers, didn't they?
Completely. They believed the entire universe, all of reality, was built on the harmony of whole numbers and their ratios. Fractions, basically. Everything could be expressed as one integer divided by another. That was fundamental to their worldview.
And then someone ruined the party.
Someone from inside their own group, supposedly. A guy named Hippasos of Metapontum. He was looking at something incredibly simple. the diagonal of a square with sides of length 1.
Which we know is the square root of 2.
Exactly. And Hippasos managed to prove mathematically that square cannot be written as a fraction. It cannot be expressed as a ratio of two whole numbers, no matter how large you make them.
Which completely contradicted their core belief.
Shattered it. If this simple geometric length didn't fit their numerical harmony, then their whole model of the cosmos was flawed. This wasn't just a mathematical quirk, it was like a cosmic heresy.
And the story goes, they weren't happy.
The legend is pretty dramatic. It claims his fellow Pythagoreans were so horrified by this discovery, this leak of dangerous truth, that they threw Hippasos overboard from a ship and drowned him.
Seriously, over a math proof.
Well, that's the legend. Historians are a bit more cautious, maybe just expulsion from the group is more likely. But the story, true or not, captures the intensity of their rejection. How deeply disturbing this idea was.
A number that exists geometrically, but can't be captured by their perfect ratios. I can see why it was a crisis.
It really was. But, you can't undiscover something. Irrationals were out there. The Greeks found ways to handle them, mostly through approximation. They got incredibly good at finding fractions that were very close to numbers, like square root of 1, or they kept narrowing the error margin.
But they didn't quite accept them fully. Like, people knew it was about 3 and a bit for ages.
For millennia. The Babylonians estimated it around 3 1/18. Archimedes famously pinned it down between two fractions, but proving definitively that Arial is irrational. That didn't happen until 1770. Johann Heinrich Lambert finally nailed that proof. Took a while.
Okay, so irrationals were a huge hurdle. But maybe even stranger conceptually was stepping off the number line entirely. I'm talking about imaginary numbers. The square root of -1.
Ah, yes, the imaginary unit. And what's really cool about Wire is that it didn't just pop out of someone thinking abstractly, what if? It actually emerged, almost accidentally, while people were trying to solve very concrete problems, cubic equations, equations with 6/3s in them.
How does solving for x lead you to the square root of a negative number? That seems like a leap.
It came from the formulas they developed. In the 16th century, there was this famous mathematical feud involving Tartaglia and Cardano over a formula to solve cubics. And when Cardano started using Tartaglia's formula, he found something weird. Sometimes, for equations where he knew there was a perfectly normal, real answer.
Like you could see the answer just by looking at the equation.
Exactly. Like 6/3x is 15x plus 4 terrors. You can spot that 6/4 works. 4 cubed is 64. 15 times 4 is 60 plus 4 is 64. Simple. But when Cardano plugged this into the general formula, the formula forced him to work with terms like the square root of -121 torts, which seemed completely meaningless.
So the formula, the supposedly general solution, spat out nonsense on its way to a real answer.
That's how it looked initially. It was a paradox. The breakthrough came from another Italian mathematician, Raphael Bombelli. He had this brilliant, pragmatic idea. He basically said, okay, this square thing looks impossible, but what if I just treat it like any other number, apply the normal rules of algebra to it, and see what happens?
Just follow the rules even if the object seems absurd.
Precisely. And when he did that, manipulating these imaginary quantities, he found that in cases like Cardano's problem, the impossible bits, the terms with square would actually cancel each other out perfectly at the end, leaving him with the correct, real answer, like 4/400. It was like taking a detour through an imaginary world to get back to a real destination.
That's amazing. Using the impossible as a tool to solve the possible, that must have changed things.
It was a huge conceptual shift. And then, later, the great Leonhard Euler came along and really cemented their importance. Euler showed these weren't just calculation tricks, they were fundamental. He derived that incredible equation EP plus 1 equals $1.
Ah, Euler's identity, the famous one.
The most beautiful equation in mathematics, many say. It connects the 5 most fundamental constants: a base of natural logarithms, the imaginary unit, the circle constant, 1, the multiplicative identity, and 0, the additive identity, all in one elegant statement.
So wasn't some weird outlier. It was woven into the very fabric of numbers.
That's what Euler showed. It proved that complex numbers, this whole system built on square, wasn't just some optional add-on. It was essential, deeply connected.
Okay, that really shifts perspective from the numbers themselves to, well, the rules. Algebra, the structure of how we manipulate things.
Exactly. And algebra itself had a long evolution. Think about those Babylonian problems. They're like word puzzles. Find a number such that half of it plus this other number. Very descriptive.
Right, not like the symbols we use now.
That symbolic leap was huge. Francois Viet starting to use letters for unknowns in the late 16th century was a game changer. And even the plus and minus signs, we kind of take them for granted, but they likely came from German merchants marking crates with plus for surplus and Pleik for deficit. Practical origins again.
So algebra becomes less about specific numbers and more about general patterns and structures.
Precisely. And that focus on structure led to the next great wall mathematicians hit, trying to find a general formula for solving polynomial equations.
We all learned the quadratic formula in school for x in 2 plus bx plus c plus c.
Right. And mathematicians found similar, though much more complicated, formulas using radicals, square roots, cube roots, etc. for cubic $6 and quartic $6 equations. Naturally, they assumed there must be one for the quintic, the fifth-degree equation by $6 in Balors. Joseph Lie Lagrange studied the existing solutions and saw a deep connection to symmetry, the way the roots of the equation could be swapped around without changing the essential structure.
He thought understanding that symmetry would unlock the quintic formula?
That was the hope. He developed a method based on these symmetries, which worked beautifully for degrees 2, 3, and 4. But when he applied it to the quintic, it backfired. Instead of simplifying the problem, his method actually led to an even more complicated equation, a sixth-degree one.
So a dead end.
It seemed like it. And then came the definitive proof. First suggested by Paolo Ruffini, then rigorously proven by Niels Henrik Abel, and explored even more deeply by the young prodigy Évariste Galois, they prove that there is no general formula using only arithmetic operations and radicals, roots, to solve polynomial equations of degree 5 or higher. It's mathematically impossible.
Impossible again. But this time, the impossibility wasn't a number, it was a process, a formula. How does proving something can't be done push math forward?
Because it forces you to ask why. Why does it work up to degree 4 but fail at 5? Galois, in the few days before his tragic death in a duel at age 20.
Just 20, incredible.
Yeah. He laid the groundwork for answering that why. He invented what we now call group theory. It's the abstract study of symmetry itself. The reason there's no general quintic formula boils down to the types of symmetry the roots can have. The symmetries for degree 5 and higher are fundamentally different, more complex than for lower degrees.
So the failure led directly to a whole new branch of mathematics.
Exactly. Group theory, born from this impossibility, is now absolutely fundamental. It's used everywhere, from understanding crystal structures in chemistry to classifying elementary particles in physics. It's all about symmetry.
That's a recurring theme, isn't it? Hitting a wall, understanding why it's a wall, and then building something new from that understanding. Okay, let's bring this home for the listener. We've talked about zero, irrationals, imaginary numbers, unsolvable equations. How does all this ancient struggle and abstract thought actually impact our lives today? Where do we see these tamed infinities and heresies at work?
Everywhere, really, once you start looking. Take calculus, for instance. Developed by Newton and Leibniz, it's fundamentally about handling continuous change, dealing with the infinitely small, another kind of infinity tamed.
And we use calculus for.
Oh, everything from designing bridges and airplanes to predicting planetary motion. Sending a probe like Cassini to Saturn, weaving through gravitational fields, that's calculus through and through. Even something seemingly static, like the new definition of the kilogram based on a perfect silicon sphere. You need incredibly precise calculus to measure its dimensions and volume accurately.
Okay, calculus makes sense. What about that leap into higher dimensions you mentioned, beyond our familiar 3D world?
Right, Descartes gave us coordinates for 2D and 3D space. But mathematicians like Hamilton realized, why stop there? We can define spaces with 4, 5, or n dimensions mathematically, initially pure abstraction, but now. Think about describing a complex system, even something like a bicycle, its position, orientation, wheel angles. You might need 6 or more independent numbers or coordinates to fully describe its state. That's a 6-dimensional configuration space.
So it's a way to organize complex information.
Exactly. And it has incredibly practical uses, like error-correcting codes. The Reed-Solomon codes used on, say, CDs, DVDs, Blu-rays, or sending data back from space probes.
How do they work?
They essentially treat blocks of data as points in a very high-dimensional space defined by polynomials. Errors shift these points. The code is designed so that even if many coordinates get corrupted, you can still figure out where the original point should have been. It's geometry saving your music or Mars photos.
Wow. High-dimensional geometry on my CD. Never thought of it that way. And finally, chaos theory. That sounds like the opposite of math's usual order.
It seemed that way at first. The idea really refined by Edward Lorenz when he was modeling weather. He found that tiny changes in starting conditions could lead to massively different outcomes later. The butterfly effect?
Deterministic rules, but unpredictable results.
Precisely. Simple equations, complex behavior. For a long time, this nonlinear dynamics was seen as messy, something to avoid. But now we realize that chaos is a fundamental part of many natural systems. We use chaos theory to understand ecological populations, analyze stock market fluctuations, model fluid dynamics, even control lasers or design better algorithms for things like pacemakers, making them more responsive to the body's naturally complex rhythms.
So it seems every time mathematicians face something truly baffling, zero, irrationals, imaginary numbers, unsolvable equations, chaos, grappling with it, taming it, didn't just solve a problem. It blew the doors open to entirely new ways of thinking.
That's exactly it. Each heresy, once understood and integrated, became a foundation stone for something much bigger and more powerful. The history of math is the history of turning the impossible into the indispensable.
Which leads to a fascinating thought to leave you, our listener, with. Given this history, this pattern of radical ideas being rejected then becoming essential, what current mathematical concepts feel impossible or nonsensical today? Are there ideas out there now maybe about different sizes of infinity, or the lemons Gödel pointed out, or something entirely new that seem like dead ends but might actually be the key to the next revolution in science or technology? Something for you to ponder on your own deep dive.